first speaker of this afternoon or evening session is Balázs Patkós from Alfred Renier Institute of Mathematics and MIPT. And he'll talk about induced and non-induced poset saturation problems. Thank you, Balázs, for agreeing to speak. And
thank you very much. Thank you for the introduction, and thank you everyone for staying with me and joining in. So first of all, this is what I'm talking about. The results are joined with Balázs Keszeg, Nathan Lemons, Ryan Martin, and Demeter Pálvölgyi. So I'm talking about saturation problems. They always come with together with extremal problems. In extremal problems, we are looking for largest combinatorial objects, Courant problems, so the most number of edges without having a triangle, the most number of hyperedges without having in an end vertex hypergraph without having a forbidden hypergraph. And so the saturation problems ask for the minimum number of edges or minimum number of hyperedges, and of course we can have the empty graph, so that's not meaningful. So therefore we are looking for the minimum number of edges in unextendable triangle-free graphs, meaning that it should be triangle-free, but adding any new edge would create a triangle or would create a forbidden hypergraph H or whatever. And there is a big difference between the two numbers, because by the Erdős-Tonsi knowledge theorem, we know that for graphs, unless the forbidden hypergraph is bipartite, then the extremal function, the Courant function, is quadratic in the number of vertices. As opposed to that, it was proved by Cassoni and Tusa that no matter what the graph is, the one can saturate, so one can create an end vertex G-free graph such that any non-edge added would create a G, such that this graph contains only linear number of edges. And this was this result of Cassoni and Tusa was extended by Picurco for K-uniform hypergraphs, and he proved that again, no matter what the forbidden hypergraph H is, if it's K-uniform, then we can saturate it with another hypergraph having at most an order of n to the k-1 hyperedges. Okay, so this is for general introduction, and let's see our topic today. Forbidden subposet problems. Well, everything starts either with the Erdős-Radó theorem or Sperner's theorem, at least for me. So today it's Sperner's theorem. It states that if we want to gather, again, this is the starting point. So this is the extremal problem. So we are looking for a largest combinatorial object, the largest family of sets with the following property. There shouldn't be any two sets that one contains the other, so anti-chains, in other words. And we know that the best possible, or Sperner proved almost 100 years ago, that the best thing to do is to take all sets of size n-half. Then clearly there won't be any inclusion, and this is best. And this was generalized by Erdős. Then, okay, now we allow our family to have inclusions, but not too many, in the sense that there shouldn't be a nested sequence of k+1 sets. We call them k+1 chains, such that the largest one contains the second one contains the third one, and so on and so on. And then again, the construction, the extremal construction is similar. If we have only k possible subset sizes, then of course there won't be a sequence of nested sets of length k+1, so that's fine. And the largest among these is when we take the subset sizes around n-half, and the expression is this one. And Erdős proved that this is best possible. Of course, we can already ask the corresponding saturation problem, and we will have a word about that in a moment. But before, let's introduce the general framework that's introduced for today. But I mean, it was introduced in the early 80s by Gyula Katona and Tamás Tarján. And so what did we have in the previous two theorems? There were some inclusion patterns or containment patterns, and how to generalize, how to describe containment pattern in general, and one way to use partially ordered sets. So here is an example. So here on the left, you see the 3-element poset that is sometimes called V. There is a smallest element and 2 other elements that are unrelated, and they are both larger than the smallest element. And how can we realize this poset with set? Well, here are 2 possible realizations. Here, the red set corresponds to this red element, and it is contained both in the blue set and in the green set, just as here. There is a big difference. The difference is, well, this one we call an induced copy, and this one we call a non-induced copy of this poset. Why? Because here, the containments are exactly for those pairs that are in relation in the partially ordered set, and here in the non-induced copy, we can have additional containment. So the difference between induced and non-induced, that here exactly those sets should be in containment, which are, or for the corresponding elements we have relation in the poset, and here we can have some additional containment. Okay, so if we now have the definition of an induced or a non-induced copy of a poset, then of course, for any poset P, we can ask for the maximum size of a set family with a ground set of size n that doesn't contain any non-induced or induced copy of P, and these 2 extreme of functions are denoted by LA NP and LA star NP. So whenever in the slides you will see a star, that will correspond to the induced version, and when it is without a star, then it's the non-induced version. Okay, so just a sanity check. Well, for chains, it doesn't matter whether we are talking about induced or non-induced versions, because there are always all the pairs are in inclusion or are related. There is no difference between the induced and the non-induced version. And so Erdős's theorem with this notation is just the LA n of the chain poset, or the total ordering on k+1 elements, and then the number here, the expression here is just that we had in your Erdős's theorem. Okay, so what do we know? Well, for the non-induced version, it follows from Erdős's result, and for the induced one, it was actually a nice proof by Abhishek Metuku and Demeter Pavlogyi to show that the order, no matter what the poset is, the order of magnitude of this extremal function, of the right function, is n choose n half, but it is still unknown in general. Of course, for some poset it is known, but not known in general whether the limit exists for all posets. There is a conjecture. This is my last slide about the extremal problem, and then we really go for the saturation version. So it is widely believed that no matter what P is, to get the largest one, or maybe not the largest one, but asymptotically the largest P-free family, no matter whether we are in the non-induced or in the induced case, what we have to do is just imitate what Erdős did. What did Erdős do? Well, he took these levels from the middle, so all the sets of size n half, then n half plus 1, n half minus 1, as far as he could without creating a chain of size k+1. And this is the same, just instead of having a chain of size k+1, now we are having an arbitrary poset P. So we try to collect as many middle levels as possible without creating a copy of P, non-induced or induced. And the conjecture is that that is asymptotically best. And it is proved for some classes of posets, but it is wide open for general. Okay. Now for the saturation problem. So these are our 2 functions for today.
Just a short question, if I may.
Yes.
So does it mean it's just the length of the longest chain, like the number of -1?
No, it is for trees. But if you consider the diamond poset, so one on the bottom, one on the top, and many in the middle, then the largest chain is 3. And if you have many in the middle, then of course the number will increase.
Okay, thank you.
Okay, so the saturation problem. So just reminder, what we want is a P-free family with the smallest possible number of sets, such that if we add any set that was previously not in the family and now we add it, then there should be a copy, non-induced or induced, depending on which version we are looking at. So a copy of P should be born, and we want to minimize that. And okay, so a little bit of history of this problem. It's not very long. So 7 years ago appeared our first paper together with Donny Gerner, Balázs Patkós, Nathan Lemons, Corey Palmer, and Demeter Parvölgyi. And what we noticed there that, well, of course, we started with chains because those are the simplest posets, and anyhow, the extrema question was settled first for the chains as well. So why not consider those? And what we observed that here's a family. Well, an underlying set will be just the integers 1 through n. And so what we do here is take all the subsets of the first k-3 elements and all their complements. And this is saturating for a chain of length k. So this, and of course, again, there is no difference between the induced and the non-induced version. So we have a bound which is independent of n. It doesn't matter how large my underlying set. I can always do with a constant number, constant depending on the length of the chain, but a constant number of sets. So why is that so? So what kind of sets do we have? Well, we have those that are very small, that only live here, and their complement, which is again something here and everything in the complement. So why is that saturating? Well, first of all, it doesn't contain a chain of length k. Why? Because, well, actually, what we have is k-3 normal elements and 1 big element, but the big element behaves just as the normal element. So basically, what we have, like, from the poset perspective, that this is just the power set of a set of size k-2. There, you can only have a set of a chain of length k-1. So obviously, this construction doesn't have a chain of length k. But why do we have the saturation property? So what happens if we add something? So we add this green set. What does this mean that we add this green set? It means that what we have, that in this second part, in this big blob, there is something, because if there is nothing, then it's already in the family, then it's a blue one. And there is something missing, because if everything is there, then it's a red thing, so it's also in the family. So what I added, this green set, it has something in here, and there is something missing from here. So then what we can do is that, okay, now look at the first part, take a maximal chain from the empty set until here, add our new set, add everything here, and finish our chain, and then we will have a chain of length k. So it is indeed a saturating family for a chain of length k. So we obtained this, which is nice, that we know that for chains, we can do it with a bounded number of sets, independently of how large the underlying set is. The question is that how sharp is this result? How good is this family? Is there any better, or even smaller, or not? Well, for small k, so for k up to 6, it is sharp, and from then on, it is not. Even us, we could figure out that there is a better construction with this many, but it's not good again. And we had but we also figured out that's an easy lower bound. So we know that we do need exponential many sets, exponential with respect to the length of the chain. And then came clever people, Morrison, Noel, and Scott, and they improved our upper bound. So k tends to infinity. Then we have, and of course, n tends to infinity as well. So then we have that this upper bound, that the coefficient in the exponent of k is triple smaller than 1. So it is somewhere between 1/2 and 0.98. It is an open problem, probably one of the most interesting one in the field. Okay. What else was known before? Well, there are just 3 more papers before ours. There is a paper with many authors: Ferrara, Cray, Kramer, Martin, Reininger, Smith, and Sullivan. And all these papers, then Martin, Smith, and Walker, and very recently Ivan, just a couple of days before our manuscript went on archive, and they all considered the induced version. And some of them noticed that, well, if we consider the appropriate, the corresponding non-induced one, then everything is trivial. And it was just a side remark in their paper. So they all considered the induced version, and they found lower bounds that grow together with n. So it's all their examples that they considered, the size of the grounds that did matter. So now to our result. So our main result corresponding to non-induced version, that yes, I mean, in some sense, these people were right not to consider the non-induced version, because whatever we have, there will be I mean, whatever the poset, the forbidden containment pattern, inclusion pattern, we can saturate that with a constant number of sets. So constant, which is independent of the ground set, but of course it does depend on P. So the bound is 2 to the size number of elements in P minus 2. Okay. First of all, this is relatively sharp because of our lower bound from long ago. So it cannot be much improved. And because of that, we have this conjecture that for non-induced versions, among k-element posets, the hardest to saturate, that is with the largest saturation function, this is the chain. This is again a conjecture. Okay, now some words, not too much, not too many, about the proof. So what we do is what we call the greedy Codex algorithm. The greedy is greedy. The Codex has something to do with the Codex, but even if you know both words, you might not be able to figure out what we meant here. So let me explain briefly. So greedy is greedy. That means that we consider all the subsets in some order, and then we try to add the sets one by one. We add the KS set if together with the already picked set, it doesn't create a non-induced copy of P. If it does, then of course we can, because the saturation includes the pre-freeness property, so there shouldn't be any copy. So we only add when it is possible to add. And then of course, at the end, if we consider all the sets, then at the end we get the P-saturating family because it will be P-free, because we always cared about not to add anything that would create a copy of P. And also, whenever we didn't add something, we didn't add it for some reason, because it would create a copy of P. So therefore, it is indeed, I mean, our resulting family will be indeed P-saturating. So it's going to be P-free, and whenever we add something that wasn't added, it would create a copy of P. Okay, so this is greedy, and now we just have to specify what does this mean, this sum order, where there comes the Codex ordering, so colexicographic. Probably most of you know it. So the finite subsets of the positive integers can be ordered in the following way. If we have two sets A and B, then B is larger than A if and only if the largest element of their symmetric difference belongs to B. So for example, here we have A and B. The symmetric difference is 1, 2, 3, 7, and 8. The largest of them is 8. 8 belongs to B, so this B is larger than A in this colexicographic ordering. Okay, so how does this go? So the empty set is the smallest element, then singleton 1, singleton 2, 1, 2, singleton 3, 1, 3, 2, 3, 1, 2, 3, and so on. This is the colexicographic ordering, I mean the initial segment set. Okay, so this could be one approach to take the greedy algorithm with respect to this Codex order, but this is not what works. But instead, what we do is that, remember, we have a ground set of size n, and then we take the first half of the Codex ordering. So that means we take the first n-1 elements and their subset, and we take the corresponding Codex ordering. So F1 is the empty set, then F2 and so on up till F2 and 2 to the n-1. And then the remaining set is basically, they are reversed. So that means the GI is the complement of FI, and then, so that means the FIs are all the sets that do not contain the last element, and the GIs are those that do contain n. And then the greedy Codex algorithm considers the set in this order. That first I take the first element or first set in the Codex ordering, then I take its complement. Then the second set in the Codex ordering, then its complement, and so on. So how does it work? So it means I start with the empty set, then with the whole underlying set, then with singleton 1, then its complement, singleton 2, complement, 1, 2, complement. And the last pair is going to be all the integers 1 through n-1 and its complement, which is just the singleton n. So in this order, we take the elements and we claim that this is what's going to happen. We will never have more sets in the family than this number, the number of elements minus 2. Okay, so this is just repetition. So what happens here, so actually we have a little bit stronger statement. What we claim is that if we measure the process in rounds, where one round contains one pair, so the corresponding Fi and the corresponding complement GI, so the one that then after the first 2 to the k minus third pair, we will never add anything. So it's not just that we won't have too many, but actually whatever is added is from the beginning. And which is nice, because if you are still with me, then you can ask that, okay, well, what is the first 2 to the k minus 3 pairs? Well, it's just the construction that I showed you like 10 minutes before, 10 minutes ago. So the subsets of the first k minus 3 elements and their complement. So what we found about 10 years ago, that's in some sense a universal construction. So no matter what P is, if P is a k element poset, then we can find within this construction, among these sets, we can find a saturating family for that particular P. I don't have too much time, so let me just give you one hint how this goes. So suppose that in the greedy process, we are trying to add this singleton, this green dot. Then, and suppose we can't do that because this is what we do, because a P is created. Then can we say something about this other singleton or this other set of size 2? And of course I claim yes, because why would I put it here otherwise? So what kind of sets are considered so far? Well, this is a singleton, so whatever was considered before is either something that comes before in the Codex order or a complement of such a set. So that means it's either is all here or it contains the whole complement. So that means this green dot behaves exactly the same way compared to these blue sets. Well, actually they are disjoint, so there is no containment, and it is contained in any kind of a red set. And this the same holds for the purple dot or for the set of the 2 black dots. So if this is not added, then it's because with this one, I would have a copy of P. But then I can replace just this guy with the 2 dots, the set of the 2 black dots. So then again. So I can say this is in a counter-positive way, which means that if later on, I would add the 2 black dots, that means I must have added the green dot. And which means that, and we can have several statements of this type, saying that if I add something, then before that, I must have added this and that and that. And based on these kind of things, if something is added later on in the Codex process, then based on that, we can create a chain of length k. And because we are in the non-induced case, and a chain of length k contains any poset on k elements, and therefore it's a contradiction to the fact that it is P3. So this is how the proof goes, and this is all I want to say about non-induced results. So what do we know about induced results? Well, much less, basically nothing. So as I said before, our work, it was only the chain that was known to be a bounded saturation, known to have a bounded saturation number independently of the ground set size. But this lemma, although it wasn't stated like this, it appears in the work of Ferraro and others, and it states that 2 things are equivalent. The one is that a poset behaves like the chain, that is, there is a constant bound on the saturation number, or equivalently, for some m, there is a saturating family that doesn't separate 2 particular elements of the ground set. So what does it mean? Separating, it means that this blue rectangle separates x and y because x is contained and y is not. So if we have a saturating family and 2 elements that are not separated by any of these sets, then that's a proof for the fact that it's going to be, the induced saturation function is bounded by a constant. And the statement of the lemma is that this is if and only if. Okay. So what are the consequences of this lemma? Well, first of all, because it's an easy fact, and probably most of you know it. I mean, this is just binary search, that to separate a set of size n, we need at least log n many sets. So that means either the induced saturation number is bounded by a constant, or it's at least log n. So that means you cannot create a poset P for which the induced saturation function is something like log n or inverse Ackermann or anything like that. It's at least log n. And actually, we believe that something much stronger is true. We believe that it's either bounded by a constant or it's at least linear. But this is just a conjecture. Let me skip this. Another consequence is that if you want to prove that the induced saturation number is bounded by a constant, then you can just come up, well, I put here that run the greedy Codex algorithm, but if you prefer, well, it's up to you. Whatever way you can get, if you have a saturating family that doesn't separate two elements, then you are done by that lemma. Then you prove that for that guy, the induced saturation function is bounded by a constant. But of course, if you cannot, or if your favorite algorithm like mine, the greedy Codex algorithm, doesn't give this, then it's bad luck. Then you didn't prove anything. And still, sometimes it's worth looking at it because, for example, there is this poset, particular poset called the butterfly poset. So 2 elements on the bottom, 2 elements on the top. So AB is smaller than CD, and these are all the relations. And what we proved, analyzing that what is the output of the greedy Codex algorithm, we could just somehow make a structure in what we saw when the output was listed. And then because of that, we could prove that the saturation number is not more than 6 and minus 10. And as I said, just a couple of days before our manuscript went online, a PhD student, Ivan from Cambridge, just proved a linear lower bound. So now we know that the induced saturation function for this particular process is linear. And then one can ask that whether the greedy Codex always gives the right order of magnitude. Well, of course not. We have lots of counterexamples. Okay. So as I said, there are lots of things that we do not know. I assume that this is one of the simplest looking posets. So we have the chains. Well, this is just lots of pairs, comparable pairs. I mean, 2 pairs are incomparable, but there are pairs. So one is the reds are smaller than the green dots and so on. And this seems to be very simple, well, as posets they are, but we don't know the answer. And of course, not the complete answer, just the fact to decide whether the induced saturation number is bounded by a constant or it grows with n. And our conjecture is that this depends on the parity of k. So we conjecture that if k is odd, then this tends to infinity. Then it is bounded. And if k is even, if you have an even number of pairs like that, then the induced saturation number is bounded by, then it's unbounded. So what do we know? So as I said, this is a conjecture. So what do we know for odd? These are the cases when we want to prove that there is a bound. So here, all we need is a construction. And we had a nice construction. I don't go into details because I only have 2 minutes. So it worked for k equals 3 and 5, but it didn't work for k equals 7. And then we used the greedy Codex algorithm, and then that worked for k equals 7 as well. So that's the only reason for which you conjecture that for odd case, this function should be bounded by a constant, of course, depending on k. What do we know about the even k? Well, we know that we know 2 things: that the greedy Codex doesn't give anything good, so it's I mean that gives an unbounded sequence of families, so that grows. And all what we could prove that yes, for k equals 2, so if we have 2 pairs, then the number is between n plus 1 and 2n. So it is indeed linear, and it tends to infinity with the ground growing. Okay, so I have one. So let me just say that we have no idea of any characterization for or how to decide whether for a poset P this induced saturation function is bounded or tends to infinity with the ground set, with the size of the ground set. We have some sufficient conditions that show that if this happens, then it's infinite, or if that happens, then it's bounded. So let me just show you one. And instead of telling you the exact theorem, I just rather point to the consequence. So in the previous example, I had many chains of length 2, so many pairs. Now I have many chains with some length. So the first chain has length I plus I1, the second chain has length I2, and so on. And what we know from a theorem that if the longest chain is at least 2 larger than all the others, then actually it is bounded by a constant. So we have some information, but we are far from knowing any general, having any general ideas when is it bounded or when is it unbounded, the induced saturation number. So thank you. That's all I wanted to say.
Thank you, Balázs. Any questions?
So I would have a question. So for the induced saturation, so do you have any, so in general, do you know any upper bounds that it's at most linear or at most polynomial, or is anything like this one?
No, we don't.
Okay.
We don't.
Yeah, actually, I also wanted to ask the same question.
Yeah, and of course, I mean, it should depend on the ground set size, so it should be polynomial or whatever in both in the size of P and in the size of N, but we don't know. Or what we know that for the greedy Codex algorithm, it seems that there are some posets for which it grows exponentially with respect to the ground set size. But just because the Codex algorithm doesn't give you anything good, it doesn't mean that it has to be that bad. So we don't have anything in general.
Great, thank you.
But here on this slide, actually, plus stands for disjoint union, kind of.
Yes, disjoint union in the sense that they are unrelated. So it's like, let me just, I mean,
yeah, like the pairs.
So like this, just with longer chain.
And since you are here, also another question. So why would you think? Can you speculate about why odd and even would be so different in this situation?
So it didn't. So all what we tried, it worked for the odd case, and it didn't work for the even case. And of course, for some, or yeah. So I mean, we really don't. Apart from having the greedy Codex algorithm and that one particular construction that worked for small values of odd case, we don't have anything. But they didn't work out for even case, and for k equals 2 we could do. But I mean, I wouldn't bet too much money on this.
And another question that I have is about the non-induced version. So what's the difficulty with proving that CK is should have the largest saturation number? So you said that greedy Codex gives this kind of automatically. If you apply greedy Codex, then
yes. If I apply greedy Codex, then we know that that the outcome family will be the largest for the case of the chain. But we know from the results of Morrison, Noel, and Scott that actually there it's not optimal. There is a better family. So because of that, I mean, it's just a conjecture.
Okay, so there is no natural way to relate this.
Yes, and the problem is that so the improvement of these three guys were of course a very nice construction. And if you look at our paper, actually this is a nice exercise to start with. If someone wants to that are lower bound, it's like a, I don't know, one paragraph proof. So the lower bound for the chain, this is very trivial, and they couldn't improve it. I'm pretty sure they tried, because I mean, if they tried to improve the upper bound, then they're pretty sure they tried to improve the lower bound, and their paper doesn't have any such result. So we don't even know that what's the exponent, and what's the coefficient of k in the exponent of the bound for the chain. So I don't know.
Okay.
Something new would be needed.
Okay. Any other questions?
Maybe I would have a remark that our archive paper has a wonderful table where you can see summary.
Yeah, so on the archive, so it is Demeter, one of my co-authors. He just wants to mention that if you want to, we have run the greedy algorithm for many the greedy Codex algorithm for many posets, and based on that, we have lots of results, like saying that the induced saturation number is bounded, and also we collected all the known results in a table. So if you just want to know that for which poset it is known and for which poset it is anything known, then you can just go, and this is one page, a table in our paper on archive.
Okay, great. Any other questions, comments?
Sorry if you ask for comment. So for set star NP, we don't even know whether it is decidable or no, whether it's bounded. I think this is so surprising. So we can't even decide whether set star NP is bounded or not.
Yeah, so this was it. This is what one of the slides that I skipped because of my time constraints. So because of that lemma that I ran through, for the fact that that the induced saturation number is bounded, there is a small finite size proof, but we don't have a finite size proof for the other direction. So the question is that whether it is deciding for one is recursive or is it just recursive anyway.
Yeah, that's surprising. Okay, so let's thank Balázs.